Dear ladies and gentlemen, dear colleagues, I welcome all of you at the webinar of use of ultra-high performance concrete in structures. My name is György Balázs, professor of structural engineering at the Budapest University of Technology and Economics in Hungary. I am honorary president at the moment. I served FIB president in 2011 and 2012. I am chairman of FIB Commission 9, Dissemination of Knowledge, where this webinar belongs to. FIB, Federation of Structural Concrete, is a pre-normative association with the main objective of producing model codes for design of concrete structures. We have model codes of 78, model code 90, 2010, and we are finishing model code 2020. FIB activities are supported by 43 member countries of 5 continents all over the world, and we hope that you will belong to these countries in the future at least as well. Model codes are used by many engineers and can be used by all codification institutions. We are happy to work together with ACI, RILEM, YAPSE, and CEN as well. We are contracted with CEN. We would like to solve a lot of questions together with these associations. Today, we have 2 excellent speakers. I would like to present them briefly. Raad Abdul-Aziz and François Toutlemonde. Raad Abdul-Aziz has the PhD degree in 2002 from Baghdad University, College of Engineering. Title of the thesis, Dynamic Analysis of Reinforced Concrete Members by Bounding Surface Plasticity Model. 2002 and 2004, University of Baghdad College of Engineering activities. He worked then as a professional engineer. He has a good balance of academic and practical engineering. He organized various webinars for ACI, CIA, Swiss engineers and architects, YAPSE, and FIB. François Toutlemonde, he works at University Gustave Eiffel, Materials and Structures Department, Marne-la-Vallée, France. From 2020, he is Deputy Director in charge for research and development. He did his PhD in 1994 at the École Nationale Pont de Chaussée, Paris, France. He supervised 15 PhD theses and 5 postdoc projects, about 20 expert studies and investigations in the field of concrete structures and engineering, especially application of advanced concretes. 75 scientific papers he published in peer-reviewed journals, over 6 books, technical guidances and recommendations. Chair of technical conferences of ACI Paris chapter, 1 per year since 2009, with 80 to 150 participants. Co-chair of international conferences, very well-known conferences, and some of them I was able to participate. CONSEC 07, 2007, concrete under severe conditions, environment and loading, sorry. CONCREC 3, together with GCI and RILEM together, international workshop. UHPLC 2013 in Marseille, CONCREC 5 with GCI and RILEM together. This was organized in Tokyo, and UHPLC 2017 is the well-known conference organized by AFGC, FIB, ACI, and Ryland together in Montpellier. The webinar today, the use of ultra-high performance concrete in structures, has been prepared for Building Research Center and Ministry of Construction of Iraq. Therefore, we have translation into Arabic language all along the presentations. In blocks will be translated. We have 4 important blocks today. There will be a short presentation by Raad about FIB, which will be followed by the presentation of François Toutlemonde, detailed presentation of UHPLC and applications as well. But there will be a part of the presentation by Raad, some of the applications. And then you can have your questions within a half an hour and comments if you want. So there will be open discussion for anybody who is interested to participate. And then we shall have a short closing. I hope that you will enjoy our program today. It will be, I hope, very useful and memorable. I have seen all the presentations. I'm absolutely sure you will enjoy it. So I kindly ask Raad to give his first presentation. Please.
Thank you very much. First, I will speak in English so everybody can understand. First of all, I would like to thank FIB and all of you here, because you who adopted this project, this presentation. So I'm very thankful for you. And also I'm very thankful to Building Research Center in Baghdad in Iraq, and especially to Dr. Suhair Kadhim al-Haboubi and Dr. Mohammed al-Musawi, who also sparked the idea of this webinar, maybe with series of webinars. So let me move in Arabic, sorry to that. So this is a small presentation about the FIB. So FIB, this is the first part of the presentation. I will present what's FIB exactly. Sorry, I will change in Arabic. مرحبا جميعا. في البداية أود أن أشكركم على قدومكم إلى هذا الويبينار. راح يكون الويبينار مقسم من 4 أجزاء. الجزء الأول هو البرزنتيشن، راح أقدم ما معنى ال FIB، introduction، تقديم إلها، شنو نوع الببليسيتي اللي عندها، وكذلك الايفنتس الموجودة. then بعد ذلك راح يكون هناك برزنتيشن بروفيسور فرانسوا تولموند، برزنتيشن راح تكون أكثر تفصيلية، ثم أعود لأقوم بتقديم بعض الابليكيشنز، الاستخدامات لهذه الماتيريال في سويسرا، وبالنهاية راح يكون هناك أسئلة من حضراتكم. ما هي FIB؟ FIB هي باللغة الفرنسية Fédération internationale de béton، معناها هي الاتحاد الدولي للخرسانة الإنشائية. هي مقرها الرئيسي في لوزان، قريبا من لوزان في سويسرا، وتشمل 41 مجموعة دولية من 104 بلدان، 104 بلدان مختلفة بالعالم. احنا حوالي 1000 عضو في هذه الجمعية، وأيضا هناك مجموعة جروبس لأعمال تقوم بأعمال داخل هذه الجمعية. هناك 11 جروب، من بينها جروب للمهندسين الشباب. أتمنى أن تكونون فعالين أيضا في هذه الفعاليات. الجمعية أو الاتحاد الدولي أنشئ عام 1998 باندماج نوعين مكانين من اللجنتين الحقيقة، هي اللجنة الدولية، اللجنة الأوروبية للخرسانة الإنشائية CEB، اللي هي أساساً تم تأسيسها عام 1953، والاتحاد الدولي للخرسانة المسبقة الجهد اللي هي مؤسسة عام 1952. النقطة المهمة بال FIB هي اتحاد دولي، هو ما له علاقة مو اتحاد وطني مثل الكود الفرنسي أو الكود الأمريكي أو الكود البريطاني، هو اتحاد دولي يشمل خبرات وكفاءات من كافة الدول، فلذلك أعتقد من الضروري أن يكون هناك اهتمام باتجاههم. النشرات اللي تقوم بها ال FIB هي النشرة الأساسية هي الكود النموذجي 2010 اللي هو تم طبعه في عام 1913، وربما قريبا إن شاء الله الكود النموذجي 2020 اللي يقوم به عدد بإكماله عدد من الخبراء. هذا الكود هو كود مهم، اللي هو يختلف عن بقية الستاندردز لأنه يتناول أمور مهمة مثل كيفية استخدام النون لينير أناليسيس في فاينايت إليمنت أو فاينايت إليمنت في الديزاين، يقوم بطرح بعض الأمور المهمة في مجال التصميم ومجال استخدام الخرسانة. الطبعة الأخرى اللي ال FIB هي Structural Concrete، اللي هي الجورنال الرئيسي لل FIB، اللي ممكن الباحثين وطلاب الدكتوراه يقومون بنشر بحوثهم في هذه الجورنال. وبالطبع هناك ال FIB Bulletin اللي هي النشرات الاتحاد، اللي هي كل نشرة مخصصة لموضوع معين تتناوله بشكل تفصيلي. هناك أيضاً activities لل FIB مهمة، منها السيمبوزيوم FIB اللي هي المؤتمرات اللي تقوم بها، وهي تقريباً مؤتمر كل سنة ينظمها عادة الجروب الوطنية. قريباً إن شاء الله بعد كم يوم هناك الكونسبت في باريس في فرنسا راح يكون يوم اثنين، أعتقد يوم 21 من هذا الشهر هناك مؤتمر في هذا المجال. هناك أيضاً السيمبوزيوم والمؤتمرات لطلاب الدكتوراه يقومون بتقديم بحوثهم، هذا يتم إنجازه مرة كل سنتين. وبالإضافة إلى ذلك هناك ال FIB كونغرس اللي يقام مرة كل 4 سنوات. بالإضافة إلى هذه الفعاليات هناك فعاليات الكورسز، هناك ويبينارز مثل ما تشوفون الآن حاليا، هناك workshops، فهناك عديد من الفعاليات، فأتمنى أن نشوفكم في هذه الفعاليات. So this is the end of my first presentation.
I kindly ask to François Toutlemonde to give his presentation.
Thank you, Georgie. Thank you, Raad. I would like to begin with a personal word. In fact, I have to apologize because I won't speak in Arabic. I think one of the only words I know in this language is salam. So my understanding is that it means peace and health and salvation. And I would first like to begin this presentation with these words, which I address to all the you attendees from Iraq and other countries in the world. And I want to say that it's my pleasure and my great honor to give you this presentation of UHPLC in structures. That to say, I've entitled this presentation 25 years experience for a promising future. So I will try to summarize this experience, at least from what I've learned about this material and the way we can use it from the what I have seen from my professional experience at the Université Gustave Eiffel, and also with all the projects made of UHPFRC, mainly in France, and it will be complemented also by the Swiss experience presented by Dr. Raad. Okay, so this presentation will have some parts, and after each part, there will be a summary in Arabic. Based on the experience of UHPFRC in France from 1996 to now, I would like to give some words on the definitions and what is UHPFRC, a short history of the implementation of these materials for structural usage. Then I give some technical aspects of the properties of these materials and the way it's taken into account by the standards. I will give some description of fruitful or promising application fields. And we will have a special focus on UHPFRC for structural repair and some conclusions. So first, what's UHPFRC? And I will illustrate this with in my different slides with examples of this material. And you see the example of a press-stress I-shaped beam that was one of the first application of this material that was used in France for repair in a nuclear power plant in a very aggressive environment. And we have some photos with the material that is being cast or being mixed, and some shore views where you see that it's called concrete, but it's really not current concrete, and that's what I will try to explain. So what we understand in France as ultra high performance fiber reinforced concrete comes from the experience of the first mixes that dates back, so 25 years ago, the reactive powder concrete developed by Bouygues, the BSI Seracem by Eiffage, BCV by Vica, and some other materials that have now new brand names, Ductal, BSI, SmartUp. And the main properties have been detailed in the first recommendations by the French AFGC, so French Association for Civil Engineering is the French branch of FIB. The compressive strength was around 180 to 200 megapascal, as exemplified in, as given in the recommendations edited in 2002, and extended to 150 to 250 megapascal. The direct tensile strength of this material is from 7 to 12 megapascal, and what's most important, the post-cracking stress for a typical 0.3 millimeter crack opening is from 7 to 12 megapascal. So there is either hardening or softening behavior, but one of the key features of this material is that we can account on tensile capacity. So the Young's modulus is between 45 to 65 gigapascal, the total shrinkage from 500 to 800 micrometers per meter. And the consistency at the fresh state is from self-leveling to viscous with threshold. And the other notable features is that there is a favorable structural behavior due to the fiber orientation in thin plates, and of course a high dependency of the tensile behavior depending on the fiber orientation. This is described by an orientation factors, a factor called K that is obtained in the structures. Other important features, the high shock strength, the capacity of energy absorption, and the very high durability and low transfer coefficients, which are related to the low water to binder cement, water to binder ratio, sorry. Some of the mixes are fire resistant, and in general, it has a very high resistance to abrasion. So that, I would say, is the description for the design engineer, a list of key figures that will enable new things for the design. For the designation of this material, we have to distinguish two key aspects. The first one will be the compressive strength. So in the continuity with what we do for concrete, we measure it on cylinders, and so we have to distinguish thresholds of 130, 150, and 250 megapascal. And so that the vertical axis in this diagram, and the horizontal axis is the pseudo-ductile post-cracking tensile capacity. So the hardening behavior in bending, which is obtained by a sufficient fiber content. And so these are two independent criteria that are used for considering the material as UHP FRC. And that's, I think, an important concept to understand, to understand the continuity and the difference from what I would call regular concrete or regular fiber concrete to UHP FRC. So I would say our key domain is, you see the dark blue cell, we call it UHP FRC type S, so for structural use, from 150 to 250 megapascal, and with steel fibers that ensure the ductile behavior. We can have a lower compressive strength, but still this capacity, and we call these materials UHP FRC type Z. So all this category is in this category, the reinforcement is given by metallic fibers, so generally steel fibers. We can have a similar behavior with non-metallic fibers, and especially polyvinyl alcohol fibers. But I would say the structural behavior is not so much documented, so we distinguish this UHP FRC from type A. And so this in this block, we will speak of UHP FRC because the compressive strength is high enough, and this is the sign of high enough durability, and we have the flexure hardening behavior that makes it possible to use it for structures. And if we have a lower strength, it may be very interesting for other projects, but the durability and the compressive strength is lower, and we call it very high performance fiber reinforced concrete, so with a V. And we, you can see in some publications, or the term UHPC, well, which can be all these materials, but also brittle materials with not enough fibers to be ductile. And I think it's important to make this distinction because UHPC can be brittle, and for the structural use, you cannot address it in the same way. So I would like to insist on this designation because, of course, it's not really universal for the moment, but I propose it for common understanding in this webinar, and it's also useful for the future practice of what we understand. So, of course, you understand the type of fibers, metallic or organic fibers. It's related to clear physical differences. For example, in case of fire, it will be a difference. The non-brittleness threshold is a key issue for possibly dispensing with reinforcement, which we will see is a key feature. Of course, these 130 and 150 megapascal can be considered as somehow conventional thresholds, but it's related to the present accepted experience, and it corresponds to the limits of what are presently accepted design methods, and changing them would require, I would say, additional technical background. And also a warning, this technical designation may differ from the commercial designations that designate a range of materials that can extend from, let's say, for example, 120 to 180 megapascal as compressive strength. So that was for the, I would say, the generic terms that you can have heard as engineers. But what I would like to explain now is more fundamental on what is UHP-FRC. And I think what we have to really remind is that it's the result from the combination of three main ideas. And first, it's the strength and compactness improvements of the cement materials by the intense reduction of the water to binder ratio. This was made more and more possible and efficient with the R&D advances in superplaticizers and mineral additions. So in this sense, UHP-FRC, I would say, is a continuation of the macro defects free or CRC materials. It's beyond the HPC, which were developed in the and used in the mid-80s. And so this reduction in the water to binder ratio leads to modifications in the ratio between high density CSH and low density CSH. So this low water to binder ratio, I would say, modified the balance between the hydrates in the cement paste. The second main idea, of course, is the fibers. As I have said, it's really a key aspect. The use of fibers will provide the post-cracking tensile capacity and pseudo-ductility. And this was made possible thanks, I would say, to more than 2 decades of conceptual and exploratory development of conventional fiber reinforced concrete, but it was made really efficient due to the high quality of the matrix and the possibility to incorporate much higher amounts of fibers, typically 2 to 3 or 5% of fibers, while you are probably limited to, let's say, less than 1% of fibers if you have a C40 to C80 concrete. And so in this sense, UHP-FRC is a continuation of the research of the optimization of the fiber aspect ratio for controlling the crack opening by Swami and other researchers. And it was also a continuation of the trends to adapt the mixed proportioning of the material to get higher fiber content. And it was also made efficient by the development of tensile tests for the material characterization. That was one of the research results in the 1980s. And the third idea is the reduction of the natural imperfections due to aggregate, which is made possible by limiting the size of the natural aggregates and selecting very high quality materials in an optimized grading. And this took benefit of the aggregate packing models that were developed in the late 80s, for example, by de la Raad and other co-authors. And it also took advantage of the use of ultrafin additions that was developed from the 1980s, especially the silica fume that was used more and more. I would say from a human perspective that UHP-FRC is also indebted to some pioneer people that really combine the three main ideas. I want to mention Pierre Richard, Marcel Chérézy, Gérard Bérelli, Thierry Thibault, Gilles Chanvillard. And these people were convinced that the combination of these three main ideas could open the way to new horizons for the cement materials. They promoted this combination and an answer to badly answered demands. So it was necessary to reduce the local brittleness of concrete materials, which is governed by the material defects. UHPLC had to promote the industrial control in the construction processes and products. It was a possibility to optimize the use of cement in a high added value material. So it also had an economic value in terms of sustainability. And as a result, it initiated a trend, I would say, I would call it less is beautiful in the concrete architecture. And these people convinced, I would say, a younger generation where I am from, who learned the concrete science with an open window to this new frontier, with a wider view of cement material science due to this experience of UHPLC. And I would say with less framed ideas of what is concrete structural engineering due to examples of UHPLC valuable design. And so that's this experience that I would like to share with you. And I will begin with the basic steps from the history of this material. And the first step, I will call it genesis, from the laboratory to first demonstrators. So let's remember in 1990, the maximum strength in the French design code was just changed from 40 to 60 megapascal. And 5 years later, Richard and Cheresy presented at the ACI convention the BPR 200. That was the conclusion of over 4 years of industrial development of mixed proportioning and qualification. And it was also the result of major R&D works on the engineering UHPLC properties. And this led to the first 2 major applications in 1997. The Sherbrooke footbridge, so you have an illustration on the top right, and the pre-stressed beams for the renovation of the heat exchange zone in the cooling towers of Cattenom power plant in France. So about 3,000 beams and girders to support the heat exchangers. And just 4 years after, the first road bridge in Bourg-les-Valences, leading to the first recommendations on these materials. So really, it's a short period of developing the materials and having the first real size applications. And at this stage, the major features, I think, that are still valid now, well, the UHPLC at this stage were several industrially controlled patented materials. So that's a limitation that is now overcome. But what is still true is that it was markedly overpassing the highest high performance concrete available at this time. So the minimum compressive strength at this stage was 150 megapascal. Of course, the post-cracking effective capacity possibly dispenses with the traditional use of secondary reinforcement. And because of the outstanding durability, that state transfer coefficients at least 10 times lower than for CAT, it was anticipated that reduced covers could be used. And what's important for the future of this material, it was recognized that there was a common interest of all the stakeholders in scientific advance and development of relevant implementation. So UHPLC was understood, I would say, both in continuity and as a breakthrough. So the outstanding compressive strength properties promoted an extreme optimization of pre-stressing. And so the durability and lightness of pre-stressed members have appeared as main advantages to be searched in the structural applications. The absence of secondary reinforcement dispenses with keeping the systematic continuity with the traditional reinforced concrete design provisions. And so the trend was to develop plain thin UHPLC elements which appear as feasible. And finally, mixing, placement, thermal treatment, formwork technology could be kept understood in the continuity with the self-compacting concrete technology that was, I would say, emerging and being recognized at this step. So this was also very helpful to make the first applications. So I'm sorry for this introduction that was a bit long, and I think Raad, you can give a summary of what I've tried to say in Arabic now.
Yes, of course. I will do just a small summary about this because I think most of the engineers in Iraq know the English terms for structural engineering. So بالبداية بروفيسور تولموند سعيد انه يقدم هذا الويبينار الى المهندسين العراقيين، ومع الاسف هو يعرف بس كلمه واحده بالعربي هي سلام، يعني كطريقه لاستقبال الناس. الجزء الاول من البرزنتيشن اللي يقدمه هو متقسم الى عده اقسام. الاول هو تعريفات للخرسانه عاليه الكفاءه، تاريخ تاريخ لهذه الماتيريال شلون وصلت الى هذه المرحله، الخصائص والمعايير لاستخدام الخرسانه فائقه الاداء، وكذلك مجالات التطبيقيه المثمره والواعده اللي تقدمها هذه الماده. ففي البدايه بدا بالموضوع بعض التعريفات للخرسانه. الخرسانه الترا هاي برفورمانس او UHPLC، راح اقدمها UHPF. هي ماده بدات تطورها بحدود من بدايه الثمانينات. اهم المميزات بهذه الماتيريال ماده هي انه مقاومه الانضغاط لها هي جدا عاليه. الى حد سنه 2002 كان المقاومه بين 180 الى 200 ميجا باسكال، بعدين تم تحويرها بالعام 2013 من 150 الى 250. فقط مقارنه، الحديد المستخدمه في المنشآت المعدنيه هي مقاومتها توصل الى حد 270 ميجا باسكال. فتقريبا هاي الماده هي تقريبا هي حديد، بس تعامل كخرسانه مثل ما هو قال بروفيسور تولموند انه هي خرسانه بس هي مو خرسانه، هي نعاملها كحديد لكن هي تشتغلها كخرسانه. مقاومه الشد لها بين 7 الى 12 ميجا باسكال، مقارنه بالخرسانه العاديه مقاومه الشد توصل الى حد 3 ماكسيموم 4. فتلاحظون الفرق الكبير في المقاومه. البوست كراكينج ستريس اللي هي عمليه جدا مهمه بعد حدوث اول التشققات الاولى، تبقى ايضا بين 7 الى 12، وهذا هو ما يعادل ما يسبب وجود الهاردنينج او السوفتنينج اذا راح يكون. طبعا اللي يحدد راح يكون هاردنينج او سوفتنينج هو كميه الالياف الموجوده بالخلطه الخرسانيه للUHPF. طبعا هذه نقطه جدا مهمه في مجال البريتلنس او الدكتاليتي، التصرف الدكتال لهذه الماتيريال. هناك معلومات اخرى اعتقد موجوده بالسلايدز، راح تشوفوها ان شاء الله في اليوتيوب. من الامور المهمه لهذه الماتيريال انها تتصرف بشكل جيد مع ان تكون ثين بليت. التصرف لها يعتمد بشكل اساسي على الاورينتيشن او التوجه اللي موجود في الالياف داخل هذه الخرسانه، اللي هو ما يسمى بالاورينتيشن فاكتور كي، وهذا عامل جدا مهم. الجزء المهم بالUHPF هو الديورابيلتي، انه هو ماده تضعها وتنساها مثل ما نقول راح نشوف في امثله اخرى. بالنسبه للتسميات او التقسيم انواع الخرسانه مثل ما قال البروفيسور تولموند، هذه لحد الان ما تم توحيدها لكل الدول. مثلا في فرنسا يستخدمون تايب اس، تايب زد، او تايب ام للفايبر المعدني، للالياف المعدنيه، او تايب اي للالياف العضويه. في سويسرا مثلا يستخدمون تسميات اخرى يسموها يو 0 يو 0 يو اي يو بي. هناك اختلافات في هذا المجال. طبعا الالياف المعدنيه هي الياف اكثر مستخدمه اكثر في مجال الهندسه الانشائيه، لانه هناك ابحاث اكثر في هذا المجال. اما الالياف الاخرى، الالياف العضويه اللي تستخدم بها بعض الالياف العضويه اللي غير ميتاليك، ما اكو بها بحوث كثيره في هذا المجال. ربما هذا نقطه مهمه باحثين في العراق يستخدموها مثلا في استخدام الالياف القديمه في اللي يستخدمها البابليين والاشوريين. هناك جزء آخر يجب أن أسرع أيضا. بالحقيقة تطوير اليو اتش بي اف تم تطويرها من 3 أفكار رئيسية. الفكرة الرئيسية الأولى اللي تستخدمها هي عملية التحكم بالووتر، ما نقول ووتر سيمنت ريشيو، بالووتر تو باوندينج ريشيو، اللي هو كيف يتحكمون بها للحصول على مواصفات، على مقاومة أكبر. هذه الفكرة الأساسية الأولى. الفكرة الأساسية الثانية هي استخدام الفايبر، الألياف، للتحكم في مجال البوست كراكينج تنسال بيهيفير اللي راح تصير. هاي هي الفكرة الثانية. الفكرة الثالثة اللي ساهمت في تطوير هذه المادة هي التحكم في مقدار او نوعيه الاجريجيت او المواد الركام الموجوده، لانه الركام اذا كان هناك بها بعض العيوب راح ياثر بشكل كبير على المواصفات الماده بشكل نهائي. هناك بحوث خلال فتره الثمانينات والتسعينات، بحوث كثيره في فرنسا وباقي انحاء العالم ساهمت في تطوير هذه الماده. ولكن سنه 97 كانت نقطه مهمه، لانه تم استخدام الالترا بيرفورمانس فايبر رينفورس كونكريت في اول فوت بريدج، في اول جسر المشاة في كندا في عام 97. ايضا في محطه توليد الطاقه الكهربائيه، محطه نوويه في فرنسا، تم استخدام هذه الماده بشكل مباشر. فاعتقد اني ارجع حتى.
Thank you. I will give now some illustration of the, I would say, the short history of implementation of this material. Let's come back to the 2002, where we have the first recommendations for designing and using this material. And for first decade, I would say the keyword is exploration. So architects and engineers tended to find the proper shapes in applying these materials. And so I'll try to illustrate this in this phase with first domain, which is application to bridges and mainly foot bridges. So you can see pictures of the Sakatamirai footbridge in Japan, the arch bridge called the Seonyu footbridge in Seoul, Glenmore footbridge here in Canada, and a small road bridge overpassing a motorway in France, La Chabot Bridge. So this type of structures, as you see, these are pre-stressed boxes or very thin shaped pressurized concrete bridges. And execution of these structures motivated a consistent research efforts to ensure controlled quality of the material produced and placed, optimization of the methods of execution, and of course, safe design provisions for lighter and thinner structures. Some further examples of bridges and footbridges. The Pinel Bridge here made of inverted T-shaped beams, so optimized shape to widen a road bridge. Here you can see the cross-section of the Passerelle des Anges, Pont du Diable footbridge. Here you see the bridge itself, where you see only lateral girders and some cross beams constitutes the frame of the structure. So there was the research of optimized shapes, so such type of beams, reef slabs, which demonstrated as favorable for variable implementation of the material. And in all these cases, the cost efficiency also relied on indirect material savings or light net benefits for the method of execution. Which was not fully expected was in this exploration period, the use of UHPFRC for architectonic applications, mainly for cladding or roofing the buildings. So here you see the Galleria Navarra roof made of very thin elements, a bus center where the walls and the roof are in a continuity of very thin shell elements, and the first application of net panels in a theater in Chartres, Les Enfants du Paradis, in 2007. So it was the discovery of new aesthetic possibilities associated to the durable mineral surface quality of this material, lightness and possible complex shapes, and a kind of semi-transparency with these net panels. And this leads also to the development of the use of UHPFRC with organic or stainless steel fibers because of the durability of the aspect. And it leads to an extended range of mixes addressing the fire-resistant demand for buildings, and also a possible compromise between these properties and lower strength requirements. And it also led to the development of ribbed plates or shells, which is very efficient structurally, with either pre-stressing or passive reinforcement in the stiffeners. In this period, so between 2002 and 2012, there was the first applications of UHPFRC for strengthening or retrofitting. So here you see the very light and thin columns in the Albi Museum. The column jacketing here for bridge to prevent the shocks from rock due to the river flow. Here additional post tensioning for bridge over the Vienne River, and also strengthening of a steel deck bridge. So there were really the first cases of these applications, and also anti-abrasion linings for hydraulic structures. So here the intrinsic material properties led to low added weight, and the implementation versatility to the fluidity of the material were really critical for these applications. And of course, the material cost is less critical than the structural effectiveness. So with the self-compacting ability, with the absence of reinforcement frames, and also the possibility to have very short job durations. Not only in France, but in a lot of in some other countries, were the first implementations where we see that really the optimization of technical solutions for civil engineering. So in these cases, I would say UHPLC is somewhat less visible, but it's however technically optimized, and it also corresponds to a business takeoff. So I illustrate here that the slabs of the extensions of Haneda Airport in Tokyo. Also the case of very light pre-stressed bridges in Malaysia. That is really one of the countries where UHPLC have developed the quickest and with the largest extent. And the use of UHPLC for joint fills between precast beams or deck slabs in the North American projects of what's called accelerated bridge reconstruction. And here also anchor plates for a retaining wall used in La Réunion Island. So of course, this phase of exploration was accompanied by a many-sided research effort. So I will not give all the details, but of course in my institution, we had a lot of PhD theses, both on the structural behavior, so fatigue, high strain rate behavior, the flow at fresh states, the characterization of the tensile behavior using bending tests, the effects at early age, the recyclability, the shear design, the bond of the reinforcement. You see here, for example, we have instrumented the rebars with fiber optics to demonstrate the very short anchorage legs of rebars in these materials. Of course, development of finite element molding with explicit accounting of fiber orientation, which is really critical. And this research was not only at the material scale, but also with the integral qualification of new solutions. So you have here, for example, the qualification of reinforced free anchor blocks for post-tensioning, development of timber UHPLC composite solution for short bridges, development of UHPLC overlay to stiffen steel deck bridges, or here you have a test of a column with both an axial compression and the effect of a seismic load transversely applied. So I would say the year 2013 corresponds to a milestone for UHPLC in France after this phase of exploration, where, well, of course, we had an international symposium on this application, but we were also able to make a revised edition of the recommendations, taking experience of all these projects. And what's important, we also have the inauguration of two iconic projects associated to urban renovation, so the MUSEM here in Marseille, and also the Jean Bouin Stadium in Paris. And this made really a wider awareness of the technical and architectural capabilities of UHPLC, both among the professionals, that's the architects and the engineers, and for the public, including the clients of the constructions. And also the technical acceptance of the design of the industrial processes and details associated to these large projects, as well as the previous satisfactory experience of building components and bridges made UHPLC, made it possible to launch the standardization process in France. So some illustration of these key demonstrative structures and applications. The MUSEM, so it's a museum on the Marseille harbor. For this project, there were more than 300 net panels for the facade, about 2,000 square meters of thin deck slabs, more than 300 tree-shaped columns, post-tension columns, 2 footbridges that you see here, about more than 70 meter span. And here what you see, the hangers for the external decks. Main lessons of this project is that, of course, these were mainly precast elements assembled on site. For the realization, the UHPLC flow was turned out to be optimized during casting, and this was, I would say, quantified with the fiber orientation factor, which had to be recalibrated for each project in relation to this optimized casting process. So there was also which is also important for the development of a material, an international recognition with the ACLI Excellence Award for the museum in 2015. And also the same year, so the Jean Bouin Stadium obtained the recognition for the category decorative concrete for the same ACI Excellence in Concrete Construction Award. In fact, for this project, you see the facade and the roof are in the continuity with more than 10,000 square meters of roofing panels and about 2,000 facade net panels. And of course, such quantities impose the industrial optimization. So there's a chain between characterization of the material, design optimization, optimization of the casting process to avoid the disturbed flow zones without the fibers, especially because the net panels had to receive glass blocks in between. So it was really necessary to demonstrate the ductility and the structural continuity of these elements, of course, because an issue of public safety that had to be demonstrated. I just mentioned in the same period the renovation of the Chillon viaducts, but Dr. Raad will give more explanation of these really demonstrative applications of UHPFRC for bridge rehabilitation. And also a very iconic structure, which is the Notre Dame de Lorette Ring of Memory in northern France. It's a memorial for about 600,000 soldiers dead during the First World War in northern France. And so it's a kind of, it's a promenade within a ring, but you do not see the ring except you see from above. And this is a pre-stressed structure because the ring is like a covered bridge for about 120 meters. So with this type of very outstanding structure, there was a full implementation of the revised recommendations for UHPFRC, especially because of the optimized use of post-tensioning with very tight geometrical achievements. You see here the size of the segments.
I think I will, because the explanation is very clear, I will just give the headlines of this part. Dr. Professor Toutlemonde فقط أعطى عدد من الأمثلة التي تم إنشائها خصوصا بين عام 2002 إلى حد 2013. خلال هاي الفترة 2002-2013 تم بناء عدد من جسور المشاة فوت بريدج، عدد من الأسقف للأبنية وبعض المدارس. تم تقوية وتدعيم بعض من الانفراستراكشر البنى التحتية في فرنسا، ومشاريع مختلفة أخرى. لكن في عام 2013 كان هناك جزء جدا مهم حدث لهذه الماتيريال الخرسانة فائقة التصرف، وذلك هو في عام 2013 تم إصدار أول مواصفات لهذه المادة في فرنسا. والشيء الثاني هو الميوزيوم الموجود في مارسي اللي هو الفساد جدا بديع مصنوع من مادة UHPLC. فهذه البيريود من 2013 بدأ استخدام هذه المادة UHPFRC بشكل مختلف. Yes, Professor.
So let's have now more detailed explanations of the UHPFRC properties as described from the standards. So the motivation for the standardization appeared as a key step for the growing business that was made possible by the successful application that I presented. So the idea was to clarify which should be the specification, which are the accepted design rules, to have I would say a fair competition in the solutions, to have an easier acceptation of the UHPFRC solutions from the owners and also from the insurance companies. And so there was a growing awareness of all interested parties, and so the standards could be elaborated in groups with all the stakeholders and experts represented. And of course, the standards were also more easily developed based on the consensus of what we had in the recommendations that were and the consolidated experience gained from the 15 years before. It was a search with the standards to comply with the FIB Model Code 2010 principles that were available at this stage, and also with the format of European standards, which made it easier for the implementation and understanding at the international level. And what's also a key aspect for the standards elaborated in France is that we needed wide purpose standards, because the applications were not focused on one typical application, like the thin layers for repair and protection in the Swiss SCIA 2052, or not like for the FHWA recommendations for the use in joint fields or bridge connections. And what's also important as compared to other standards under development is that the acceptability for construction was conditioned by the fact that only non-brittle materials would be covered by these documents. And of course, I would say the case-by-case technical evaluation or approval remained a possibility for more innovative projects or other projects not covered by the standards. So let's have a look on the architecture of this French standard. The first two standards published in 2016 concern the design. So it's a national addition to Eurocode 2. So not to repeat all the things that are useful from Eurocode 2, but all the specific clauses are detailed. On the contrary, the standard corresponding to the material, so what's called the product standard in the European standardization language, corresponds to specification, performance, production, and conformity. And it includes in annexes some specific features for the tests to qualify the performance of UHPFRC. And it addresses both the UHPFRC for structures and for non-structural or architectonic applications. It covers UHPFRC either based on premix or non-premix recipes. It addresses on-site prefabrication in a precasting plant, or mixed on-site or ready-mix UHPFRC. And we finished the work, I would say, with the execution standard, so which is a national addition to the European standard EN 13670. So it gives the specific rules for UHPFRC, and it's applicable to execution of UHPFRC structural or non-structural or architectonic elements. So of course, both these three standards have been elaborated in consistency. And the rules for the precast industry mention this from 2018. These three standards for the common rules for precast products made of UHPFRC. It's really a complete covering of the domain. So what's still not covered is the design of non-structural UHPFRC elements, especially made with non-metallic fibers. Because at the moment of elaborating these standards, it was considered not to have enough experience on this type of materials. I'll try to give you briefly some of the key features of these standards. So as I said, for the design, as a national addition to Eurocode 2, the frame of Eurocode is kept and many clauses are unchanged. We follow the Eurocode outline, so it clarifies the way we express the requirements. Based on the practice that was validated from the beginning of I would say the implementation of the material, the tensile capacity of UHPFRC annotation is taken into account even when cracked, and this makes necessary to define a specific partial factor. The effect of fibers distribution is taken into account with a set of orientation factors. The cover to reinforcement or tendons is reduced due to the high durability, but the quality of placement imposes a cover thickness higher than 1.5 the length of the fibers, except demonstrated more specifically. The ULS cross-sectional design is based on a diagram of admissible strain, so it's really in the continuity with reinforced and pre-stressed concrete. But the cases of reinforced or pre-stressed concrete versus plain UHPFRC have been clarified with the specific ultimate strain to be met in this diagram. And the shear design assumes an additive contribution of the UHPFRC under diagonal tension, so which is brought by the fibers, and the transverse reinforcement, let's say the stirrups, if any. And we also had to fill a gap with the seismic verification because I mean seismic resistance is a legal issue in France. So partial factors are given. The elastic behavior of the UHPFRC frame structure is admitted, and an experimental verification is required in case of a larger ductility demand. Some clauses were much improved from the previous recommendations to the standard in 2016. So I would say the clarification of the material specification in terms of design classes and what is used for the design had been much clarified. Also, the verifications related to buckling and elastic stability, which are normally not frequently critical for concrete structures, but because of much thinner elements, here it was necessary to address the aspect. There were indications were given on the acceptability of justifications based on advanced nonlinear analysis, and clause for fatigue verification were given, and also the details of shear verifications, including torsion, punching shear, with a better distinction of the cases of plain, reinforced, or pre-stressed UHPFRC members. And also the set of partial factors for accidental loadings were made explicit. Also the aspect of file design, which is also a legal issue in France, was detailed with an annex which is normative, which details the applicability of the Eurocode 2 methods, excluding the simplified rules. And the details are given to determine the material property and the control of the risk of thermal instability let's say spalling, is described, and in general a representative test is necessary. And in this case, the incorporation of polypropylene fibers is indicated as being generally appropriate. Let's go to the material standard. So it gives the minimum requirements to call a material UHPLC. So as I've said before, there is a criterion in terms of compressive strengths higher than 130 megapascal and 150 for structural applications. A minimum elastic tensile strength of 6 megapascal. A minimum non-brittleness rule, which is expressed as a post-cracking tensile equivalent stress between 0 and 0.3 millimeter crack opening higher than 40% of the elastic limit and higher than 3 megapascal. And minimum durability properties that are the water porosity lower than 9%, a chloride diffusion coefficient lower than 0.5, 10 to the minus 12, and a gas permeability lower than 9 to the minus 19 square meter. For easier specification, classes are given for the compressive strength, for description of the tensile behavior, so softening or hardening, classes for improved potential durability, consistence classes from self-compacting to viscous with threshold, classes related to the thermal treatment, and abrasion resistance classes. And it was clarified how to specify the tensile behavior, which is quite important because it's really one of the key aspects from the project to what is necessary to check from the material. So it has to be characterized by a stress crack opening or stress strain curve to be compared to the experimental estimation of the characteristic curve from molded specimens. And a set of orientation factors is given and has to be checked in the relevant directions. And this orientation factor has to be between 1 and 2.5 for the local factor, and from between 1 and 2 for the global factor. So this may lead to reconsider the way of casting the material so that the orientation of the factor is consistent with what is necessary for the tensile forces equilibrium in the project. So this leads to a special chain of conformity assessment for this type of material. We have a design study which is carried out by the producer to verify that the mix allows meeting the project requirements and is robust enough for the project. And when there is an identity card, this may replace this design study. But a key step that is not so classical for concrete in general is the suitability test, so which is part of the initial testing, and it's in fact a trial production. The aim is to verify that the required properties are met in the specific production conditions of the project, and it fixes the effective production and mixing process, but also the transport procedure, the procedure of placing, finishing, curing the material, and the protocol of thermal treatment, if any. And for this, it comprises the production of a representative prototype element carried out under the responsibility of the user of the UHPLC to check whether the specified performances are met, and especially the orientation factors. And so this is really a difference with the classical concrete, so that the user of the material is also partly responsible of the conformity of the material. And so the conformity is checked at the different relevant steps. Conformity of the premix, if they are relevant, the design study, the suitability test, and of course the control test during the productions. Some also some specific features of the execution standard, so which is a national addition to the European execution standard. So there is a minimum class 2 for the execution. That's to say, checking is mandatory and it's not only self-monitoring of the producer. So this standard was made compatible both for casting plates, UHPFRC, and prefabrication. And so the main complements or specific differences are additional indications concerning formworks because of the tightness, because of the prevention of early age restraint, because of the control of the geometry, especially when you have thin elements. What's also specific is the fact that we have a mandatory content of what's called the concreting program. So there are some indications on how it's validated. So of course, there is no internal vibration for UHPFRC. There are recommendations on how to prevent cold joints, how to address hot weather or cold weather concreting, curing, thermal treatment, control of cooling, and also provisions for casting UHPFRC against other materials. And the last main part of this standard is the geometrical tolerances. So there are two classes, and especially there are small admitted deviations for the thin members that differ from what is in the present standards. So as a conclusion of this part, what's the situation now with the standards? We can see that all UHPFRC mixes are not similar. So the list of the characteristics that are necessary for the projects is clearly longer than for regular concrete, and the prescribers have to get aware with this. It saves time to use UHPFRC mixes with identity cards, because we already have a first control or that the material properties will be met for the project. And of course, this is a matter of specific care in case of alternative bids in answering tenders. And what's important and maybe more critical than in classical concrete is the interaction between material and design. Of course, it has an incidence on costs and methods. What has to be kept in mind is that UHPFRC is not only a premix nor mixed proportions, and the suitability test is critical to validate the concreting process and program, post-casting treatments, meeting the K-factors requirements. And this, as I've said, is a matter of combined responsibilities of the UHPFRC user and producer. And so what's also important to keep in mind is that the UHPFRC technical knowledge has to be shared by the premix supplier, by the supplier of the fresh UHPFRC, which is seldom a conventional ready-mix concrete supplier, in fact. It has to be shared by the UHPFRC user, by the designer, the checker, the prescribers, and the organization or the contract situations are various, but so sometimes the premix producer is also the user and the designer, but sometimes they are different. But whatsoever, the technical results must always meet the quality levels that are expected and are requested by the standards chain for the final client.
تتقسم المواصفات اللي قدمها بروفيسور تولموند تتقسم إلى 3 أقسام. القسم اللي يتخصص للمصممين، قسم مخصص فقط للمواد، وقسم النوع الثالث من المواصفات هي للتنفيذ. فقط أحب أنوه أنه اللي ذكره بروفيسور تولموند هي المواصفات الجزء الفرنسي، لأن المواصفات الأوروبية هي مواصفات عامة لكل أوروبا، في حين كل بلد في أوروبا يمتلك خصوصياته بمواصفاته. فالمواصفات اللي ذكرت هي مواصفات فقط لفرنسا. فمثلا إذا العراق أو في دول الشرق الأوسط يحاولون يستخدمون هذه المواصفات، عليهم أن يجدون خصوصيتهم في هذه المواصفات. هناك جزء كلش مهم يجب أن نفهمه، أنه المواصفات عملية تنفيذ مشروع باليو اتش بي اف ار سي هذه مسؤولية الجميع، هي مو فقط مسؤولية المصمم ولا مسؤولية المجهز، إنما هي مسؤولية الجميع. نوعية الخرسانة ونوعية المادة اللي راح توصل وتتم تنفيذها هي يتقاسمها المسؤولية، يتقاسمها المجهز اللي هو شركة تجهيز الخلطة، زائدا المنفذ، زائدا المصمم، وحتى المستخدم نفسه أيضا مسؤول عن هذه الأمور. هناك في عملية تصميم الخلطة اليو اتش بي اف ار سي، هذه الخلطة هي مو مثل الكونكريت الاوردينري كونكريت، مو مثل الخرسانة العادية، لأنه كل مشروع كل مكان كل موضوع يحتاج الخلطة المناسبة إلى الدراسة الخاصة إليه. فلذلك كل جزء كل عملية لإملاء العقود في المقاولين هذه راح تتطلب وقت أكثر من اللي تتطلب الخرسانة العادية. هناك ما أقدر أقول ثغرة، إنما أقول أنه هناك مجال لتطوير هذه البحوث وإثبات المواصفات. هي في بعض المكانات بروفيسور تولموند ذكرها اللي بالتفصيل، هي الفواصل الكونستراكشن بين القديم والجديد، لأنه في اليو اتش بي اف ار سي لا يوجد vibration.
So I would try to give you now a picture of what can be considered as the fruitful or promising application fields of this UHPFRC material, based on, I would say, on the present trends, and especially in France, which the situation can be diverse in other countries, but it can also give you some ideas. So first, I come back to the applications in footbridges. What is search for these applications is slenderness and lightness. We have records of slenderness, for example, for the Angels footbridge here. What's taking benefit of is the performance in compression associated to post-tensioning, the performance in tension for the transverse bending and shear, and the cost efficiency for the erection with lighter false work. And what's also interesting is the architectural versatility. We have examples of truss, of P-shaped, of side beam supporting structures. For these structures, one point to be aware is the critical control of vibrations. And I think an issue for the future is the balance between, I would say, signature bridges and the replicability, which is in the sense of cost efficiency. As an example of the repeatability, there was an optimization of the inverted T-shaped beams with a widened flange. So that's the symbol of ITE in France. This shape was optimized for the processing efficiency, which enlarged the capacity of the lower flange. The introduction of the press-stressing force is shifted because there are a lot of tendons, as you can see here. There are no stirrups for shear except at the end for the highly skewed bridges. The casting takes place in 2 steps, and of course it's necessary to treat the joint. And these solutions is very durable because only high quality formed UHPLC faces are exposed to the aggressive environment. So it keeps solutions maintenance free because you have the, the lower shape of these UHPLC beams and the top of the upper flange that is also protected. So it has turned out efficient for technical projects with no necessary temporary bracing of the beams. It's much lighter than bridge filler beams. There is no exposed steel. It gives security during top deck concreting, which has been applied. So here for this bridge, which is built over a railway line. It's also possibly compatible with the expansion joint-free bridge concept. So there are 4 applications for the moment of this type of solution. And here especially the La République bridge in Montpellier, where you see the deck is made of these T-shaped beams. Another favorite shape for UHPLC application is columns, because it's a direct application of the compressive strength performance. There's the possibility of ultra-thin columns, for example, in case of buildings retrofitting. There is also the possibility of ultra-thin jacketing for increasing the load capacity. It can be applied for a self-supporting facade. Here you see for an external thermal insulation of a building. And the architectural versatility is made possible by the material performance. So with this type of tree-shaped columns. Some points to be addressed: the buckling verifications with respect to the tolerances, the fire resistance requirements, if relevant, have to be integrated. The seismic behavior and the ductility have to be assessed, and so this may require some specific justifications. And also one of the key aspects is the optimization of the assemblies when these columns are very, very high, so as to have durable and efficient solutions. One of the key market segments, I would say, of UHPLC in France is the net panels and the cladding or roofing panels. It's really an architectural trend and a kind of signature solution of UHPLC from 2007. The lightness and transparency is made possible by the material performance and flowability. The high surface quality is due to the dense material texture. Of course, it requires a key industrial know-how to control molding and restraints. So what's attractive for the architects is the mineral aspect, the durability, also the cost efficiency, because it's very light, and there are a lot of possibilities of increasing the void ratio and color variations. And the lightness, the efficiency, and durability are really increased as compared to regular concrete. There should be optimized fixation devices to the structure, so that's generally one of the key aspects of the technical control of this solution. And as I said, this is one of the most important sectors for the French UHPLC market. In the continuity of these elements, the roofing elements that are generally made of larger shells. So it's a key field of application for architecture. The lightness allows larger spans. The cost efficiency is based on the low dead weight in a global design, and attractive solutions have been developed with combination with glass. So with semi-transparent solutions, you see in the bottom right here the roofing of the Montpellier high-speed railway station, where this solution has been applied. So here again, architectural versatility has been demonstrated, and the tightness requirement may also be combined in a single, I would say, material solution without additional waterproofing layer to be applied. So some variations for this type of applications. In case of ribbed solution, depending on the span, there could be reinforcing steel or post-tensioning. There could be replates or shells. Here again, one of the key conceptual design issues is the way it's fixed on the supporting structure. And of course, it's here again demands high geometrical accuracy and high quality facings, which is an important skill of the precaster. I'll briefly mention here the connection of UHPLC for structural strengthening, because these solutions are more and more adopted because it's generally low intrusive, because the performance of the material makes it possible to keep the material addition light, and it has a limited incidence on the supports. So it takes benefit on the material performance in compression for longitudinal bending and in tension for transverse bendings on supports. And both performance are applied for the post-tensioning anchor blocks. Because of the high Young's modulus, the UHPLC additional elements may, I would say, keep the flow of forces, which alleviates what is taken by the existing structure. And of course, it takes benefit of durability, tightness, resistance to abrasion, and the compatibility with the existing steel or concrete support. The conditions, I would say, of optimal implementations is the fact that the material quantities can be saved so that the material cost is not so much critical. The material, the works execution, and the logistics have to be optimized, I would say, simultaneously. This may lead to possible short job site duration because of the rapid UHPLC hardening. And so it's quite demanding, I mean, in a global design of this type of applications. So I try to summarize the key advantages of UHPLC. Of course, the outstanding compressive strengths promotes extreme optimization of pre-stressing. So it promotes durability and lightness of pre-stressed members. The absence of secondary reinforcements dispenses with keeping systematic continuity with traditional reinforced concrete design provisions. So the mixing, the placement, and the thermal treatment and the formal technology are managed in a continuity with self-compacting concrete, and there is an increasing accounting for control of rheology and thixotropy. And the new aesthetic possibilities are really a driving force associated to the durability and the mineral surface quality of the solutions. Okay, and as I said, the implementations for repair operations is also very attractive. So I think we have the Arabic translation, and then I will focus on the use for structural repair with some examples.
I think the photos and the explanation is very clear. I will just put some headlines about this. أعتقد الإمكانيات والمشاريع اللي تم إنشائها بالUHPLC واضحة جدا. هي إما بالجسور، إما بالأبنية، في السقوف، في الفساد، وهناك أمثلة جدا بديعة. إمكانيات UHPLC إمكانيات هائلة، إنه أولا هي عالية المقاومة، ما يحتاج إلى معالجات خاصة لحماية من الرطوبة. بنفس الوقت هو ما يحتاج إلى تسليح ثانوي لأنه هو كومباكت. الأعضاء الإنشائية اللي تم إنشائها بهذه الماتيريال هي صغيرة الحجم، بالتالي الديد لود او السيلف ويت كلش قليله، في ذلك الوقت تمكنك من بالنسبه للفاونديشنز، بالنسبه للاسس، بالنسبه للممبرز اللي تقوم باسنادها، هي نقطه جدا مهمه. بالاضافه الى هذا امكانيات الجماليه لهذه الماتيريال جدا كبيره. فاعتقد الصور والمشاريع اللي تم تقديمها واضحه جدا. Yes, of course.
So here again, I think I will go briefly because the pictures are more explicit than what I can say. So some references in the UHPFRC applications for buildings repair. We have seen the renovation with very thin columns in a museum, the external facades. Here it's not so visible, but there is a thin layer of UHPFRC that about doubled the bearing capacity of these columns. Here it's in a parking because the building had to be increased in height by several additional stairs. I mentioned the steel bridge deck strengthening because we have a generic issue with orthotopic deck bridges, at least in Europe and Northern Europe, because these structures are very much sensitive to fatigue, especially at this junction between the troughs and the plate. And it was demonstrated. So these are measurements in a let's say scale 1 research program, which you see here in the laboratory, that the use of the UHPC overlay, connected overlay, could significantly reduce the stress concentrations here at these welding details. So there was applications either with cast-in-place UHPFRC in the Netherlands, in Japan, in France, and also with precast UHPFRC slabs that are illustrated here with the orthodal process. So there is a potential market for large sensitive long span steel bridges in France, in Japan, in USA, in the Netherlands. And one of the key questions is probably the optimizations of the methods and logistics for this type of job site. I will be very brief on the stiffening of concrete bridge decks because this is has been mainly developed in Switzerland from the European project Arches and Samaris, and with the example of the Chillon Viaduct and more than 100 bridges. One question for me is why this is a very important market in Switzerland and not really effective for the moment in France, although we have some zones where we have an intense use of de-icing salts, and this preventive maintenance approach would be probably more cost efficient. Here I have some illustrations of UHPFRC used for widening of concrete decks, either with ribbed slabs or with additional slabs, or here with lateral deck built over UHPFRC inverted T-beams. So this is probably a future market for the retrofitting of composite bridges, and also for the widening of urban bridges or bridges under heavy traffic because of the possibility to reduce the duration of the job site. And I illustrate with two examples in Thoiry-sur-Loire and Mauves-sur-Loire, case where we had a full deck reconstruction for these. These are long steel bridges where the deck was formerly made of brick vaults, and of course the steel beams were damaged by corrosion because these vaults the water tightness was lost, and the walls were much damaged, and they were replaced by UHPFRC slabs that you see like this, connected on site by UHPFRC joints. And this solution proved very efficient structurally because of the lightness of the deck, and it made it possible also to, in one of the cases, to widen the deck with without increasing too much the dead weight, with a lane for bicycles, which is quite attractive in some cases for the bridges in France. So here I briefly mentioned the use of UHPFRC for keying joints between precast elements in the USA and Canada, because this is this can be an attractive sector, because one of the key advantages is the rapid hardening of the UHPFRC, and the shorter anchorage length of UHPFRC with the rebars, which limits the volume of the joints and makes it possible to reopen to traffic within 1 day, which is much appreciated, especially in zones where the alternative route solutions are not so easy to find. So here an implementation of the UHPFRC for keying joints and overlay on the Pulaski Skyway in New Jersey. Also attractive is the UHPFRC used for anchoring the anchor blocks for additional post-tensioning, which has been implemented especially recently in the Hammersmith flyover in London. And this really makes it possible to have some, I would say, surgery operations for this type of bridges with a very efficient logistics, either with prefabrication of the blocks or small size on-site casting. And some examples of UHPFRC used for jacketing or protective layers. Here on a dam on a mountain flow to protect against shocks and abrasion. Here in a hydraulic tunnel in Japan with prefabricated very thin shells. Here overlay on the marine signal, and here again on a bridge pier to protect from rock shocks. So probably because of aging infrastructures, this could be a growing market. So if we try to push to list what is necessary for efficient UHPFRC application in such repair operations, of course, we have the specific features of low intrusiveness, lightness, the bearing capacity of the material itself, and the fact that the material cost is generally less critical than methods and logistics in such operations. So the advantages that are generally key aspects of the cost efficiency is the optimization of added mass, the reduction of the operation duration by prefabrication or adapted rheology if cast in place, the durability, and resistance to abrasion, and the conditions of correct implementations are the relevance with respect to possible other alternative techniques. For example, UHPFRC is more fire resistant than solutions using fiber reinforced polymer materials, for example. It can adapt to complex shapes. It keeps stiffness and bearing capacity under compression, and also there's the possibility of underwater casting. I said before, I think one of the key of the success in the integration of material design and methods optimizations, and this may induce consequences in the proper way to organize the contracts and the control of risks in such operations. I would like to mention that this is one of the field of development of the UHPFRC applications. For example, the internal jacketing of steel culverts with the sprayed UHPFRC, which is illustrated here in a prototype application. The column jacketing for seismic retrofitting, and also the use of UHPFRC to protect equipment such as sound barriers or parapets. And I let you give some comments after conclusion. I will conclude.
Yeah, exactly. It's very clear. فقط أحب أنوه أنه تم عرض بعض الأمثلة لعمليات التقوية والتدعيم لمنشآت مبنية أساسا مثل المنشآت مثل الجسور وبعض السدود. هذه المادة UHPFRC مادة جدا ناجحة في هذه المجال، في مجال التدعيم وتقوية المنشآت الموجودة أصلا. من ناحية المادة نفسها هي مادة غالية مقارنة بالخرسانة العادية، لكن بسبب حجم الأعضاء الإنشائية اللي يتم تصنيعها هي أصغر بكثير بسبب مقاومتها للحريق، مقاومتها للرطوبة. كل هذه تنطي فوائد تنفيذية أكثر بهذه المادة مقارنة بالخرسانة التقليدية. فلذلك يتم استخدامها بكثرة في عمليات التقوية. Yes, Professor.
So very briefly, some conclusions. What's the situation now? I would give a perspective of what are for me the new frontiers of UHPFRC. I think the UHPFRC offer gets wider, and there is an increased competition between the suppliers of these materials. The variabilities, the constituent sources, the possibility of having greener mixes, UHPFRC mixes, the balance between cost reduction and stable quality of the material. One of the consequences is the way we need to have a fair indication of what is in the UHPFRC offer, and what's the choice for the properties, and this may need the education of the prescribers, let's say the designers and the contractors, that will need to understand which type of UHPFRC they need for their project. And for this, of course, the standards may help, but there is still an issue of how can we consider the UHPFRC materials that are just outside of the standards or at the limit of the standards. And probably there is we have to make an effort in extending the standards to cover the materials that are relevant for other projects, but which may still not be UHPFRCs. I have to mention that this diversification of the UHPFRC is also based on R&D efforts. These efforts address the numerical prototyping for control of casting and hardening, and so having a kind of earlier and less expensive prototyping of the UHPFRC solution. There is a development of non-conventional concreting, for example, UHPFRC shotcrete or 3D printing of UHPFRC. And we can see that I mentioned it in some cases. There is a necessary know-how to be gained in the execution for molding, for the facing textures, and so on. So we are still not the full achievement, I think, on the industrial control by everyone in the sector of the full control of the UHPFRC possibilities, but it's a growing effort. Some aspects deserve necessary efforts in research for advanced or extensions of the UHPFRC design and application possibilities. I would mention the seismic design and detailing, the safe justifications based on nonlinear finite element models, the standardization of the design procedures for UHPFRC with non-metallic fibers. And I think one of the tasks we have to address now is education and appropriation of UHPFRC. It's a challenge because I don't know in Iraq, but in some countries, you know, the time which is allocated for students to learn concrete and to learn not only the design rules, but also the material science between in terms of concrete is not so long, and maybe it's not longer and longer, I would say. So one of the challenges is the dissemination of educational tools for architects, for design engineers, the development of cost-efficient, customizable UHPFRC solutions that are known, and the initial education programs to be updated so that you know, the younger engineers know UHPFRC and not only the concrete of their grandfathers. There are some questions to address now on the, I would say, cost-efficient performance of UHPFRC to be searched. One of the key aspects is how to answer with UHPFRC the high durability demand that may concern the marine structures, the protective structures, the road equipments, the industrial buildings, the urban furniture. I think UHPFRC can offer a lot of solutions, but of course we need the architects, the designers, the prescribers that can think UHPFRC solutions. Also, UHPFRC is a part of the sustainable solutions for protection or for strengthening, being a strengthening component for the bridge decks for the light cladding elements. So I have given some additional pictures that you will recognize for these for supporting these questions. And what I would say for the end is now UHPFRC is open for creativity, and you have some examples of projects that are not really classical concrete projects and that UHPFRC has made possible. So it's up to you now to know what you can build with this material. I would like to conclude with some references if you need further information, and I would like to mention that in addition, there should be soon a publication of an FIB bulletin on FRC that has been prepared, and I think we are just at the end of the preparation of the publication process. And it's FRC, but one of the chapters is dedicated to ultra high performance fiber reinforced concrete, and I think it's a lot of information in this chapter. And finally, I would like to thank you for your kind attention and acknowledge all the people I've met and worked with in this part of history of my professional life dedicated to ultra high performance fiber reinforced concrete. Thank you very much.
Just to say something, أعتقد بروفيسور تولموند ختم البرزنتيشن مات تلخيص الاليمنت المهمه بالنسبه ل UHPLC اللي هي اليمنت مهمه، في حين هناك مجال للبحوث مفتوح. اقصد انه مفتوح انه ماكو معلومات كثيره محتاجين نبحث بها اكثر، هي مجال التصميم الزلزالي لهذه المنشآت، التصميم الفاينite element analysis non-linear لهذه المادة، وكذلك هناك جهود يجب أن تكون تبذل أكثر في مجال التعليم، لأنه تعليم أو تدريس أو تدريب على هذه المادة هي مو كلش تقليدية، فلذلك ممكن نحتاج أن نطور هذا أسلوب التدريس أو أسلوب التدريب على هذه المواد بشكل أكثر، وخاصة بالنسبة مو فقط مهندسين مدنيين أو كذلك للمعماريين و للمهندسين التنفيذ. Yes, thank you.
Thank you very much, François, for your very interesting presentation. I kindly ask Raad Abdul-Aziz to give his presentation, the second one, please, and we come back for the questions and comments. Yes.
Yes, of course. I will speak. Sorry, I'll speak in Arabic to the Iraqi or Middle East members. So this is هذه هو الجزء الثاني من المحاضرة مالتي، من التقديم مالتي. راح أتكلم بشكل مخصص عن UHPC والبنى التحتية، وخاصة الطرق والجسور، وبعض الأمثلة في سويسرلاند في سويسرا اللي تم تنفيذها خلال السنوات القليلة الماضية. بشكل أساسي وين سويسرا؟ هي سويسرا هنا في قلب أوروبا، نصها مأخوذة من جبال الألب. جبال الألب اللي تقسم أوروبا إلى جزئين، جنوب أوروبا شمال أوروبا، لذلك كل خطوط المواصلات هي خطوط جدا مهمة، لأنه هي الشريان الأساسي للنقل بين الجنوب والشمال. هذه الخطوط خطوط النقل هي من آلاف السنين، من عهد الرومان. بعض الخطوط تم إنشائها من قبل يوليوس قيصر. فالنقل والبنى التحتية للمواصلات هي جدا مهمة. بالنسبة للمواصفات السويسرية، فقط حتى نوضح الأمور، المواصفات السويسرية هي مو شبيهة المواصفات الأوروبية، ما تعتمد عليها مباشرة، لكن هي مشابهة، نقدر نقول هي بتدعمها. المواصفات الأساسية هي SIA 260 اللي هي المواصفات اللي تتحكم بالمهندس كمهندس إنشائي للتصميم. لكن في للبفب أو الترم اللي هو الترم الفرنسي للألترا هاي بيرفورمانس فايبر رينفورس كونكريت، هناك دوكيمنت اللي تتعامل مع هذه المادة من الناحية الإنشائية. فهو هي المواصفات، أو نقدر نقول النوت بوك 2052 اللي يحدد وينظم التصرف الإنشائي، وكيف يمكن إجراء الحسابات لهذه الماتيريال. مثل ما ذكرنا، خطوط النقل الانفراستراكشر او البنى التحتيه للمواصلات هي مهمه جدا في سويسرا، لانه هي تخترق جبال الألب وتربط جنوب اوروبا مع شمال اوروبا. هناك حوالي 1700 كيلومتر طول خطوط سريعه، بلاند بالمستقبل ان شاء الله توصل الى حد بحدود 1900. أول خط سريع كان في عام 1955 بين لوسيرن وأورب. في عام 1960 تم تأسيس الأوفيس فيدرال دو روت أو المكتب الفيدرالي للطرق والمواصلات. معظم هذه المنشآت هي تم إنشائها في السنوات الستينات 1960 and 1970. فأول إكزامبل راح أنطي هو على بون سور بوديز اللي هو جسر فوق نهر البوديز اللي هو مكانه بالضبط هنا في بين لوزان وفيفين. هذا الجسر هو بالحقيقة مشروع، هو بالحقيقة جسرين وليس جسر واحد، تم إنشاؤه في عام 1971 إلى 1973. يتألف من 5 فضاءات. كل فضاء، الفضاء الأكبر فضاء بحدود 104 متر في هذا المكان. يتألف الجسر من عتبة صندوقية. أرض هذه العتبة هي 6 أمتار و70 سنتيم. الارتفاع العتبة الصندوقية يتراوح بين 220 إلى حد 4 أمتار و30. هذا الجسر هو تم إنشاؤه في عام مثل ما قلنا بين 71 و 73، لكن شهد مشاكل إنشائية جدا كبيرة، وبسبب طبعا بسبب الثلوج، بسبب التعرية، بسبب استخدام الأملاح لمعالجة الثلوج. فحدثت به مشاكل إنشائية كثيرة، من بينها مثل ما تشوفون هنا في الكانتليفر هناك مشاكل في صدأ الحديد التسليح، تكسر الخرسانة، هناك مشاكل في بعض الشقوق في السلاب الأسفل، في البلاطة السفلية. هناك مشاكل، بعض المشاكل في الفاونديشن، مشاكل بسيطة لكن أيضا يجب أن معالجتها. هذه بالنسبة للمشاكل. الشيء الثاني، الاستخدام للمستقبل يحتاج أن يتم تغيير الأجزاء الجانبية، الحماية الجانبية للجسر، فيجب أن يتم إبدالها بعازل خرساني حتى يحمي الطريق. وكذلك علينا أن يجب أن وضع حاجز مضاد للضوضاء. فالفكرة الأساسية هو كان المشروع هو بالحقيقة في إبدال، في كسر 1.30 متر من الجسر، قطعها وإبدالها بخرسانة عادية. هذه الخرسانة راح تكون تشكل جزء من الجسر، من مسار السير. إضافة إلى هذا علينا أن يكون أيضا مرد للحماية. حديد التسليح هنا في الجزء العلوي هو ثابت، هو نفسه الموجود من عام 1973، فما ممكن إضافة حديد تسليح آخر. فالحل الأمثل هو بإضافة عكازات لحمل هذه المساهمة في حمل الأحمال في هذا المكان إلى مكان آخر بدون الحاجة إلى زيادة حديد التسليح في هذا المكان. في البداية كان الفكرة الأساسية هو أن وضع عكازات حديدية ستيل ستراكشر، لكن بسبب ارتفاع العالي لهذا الجزء، عملية صعوبة الوصول إلى هذه العكازات، بسبب انه الستريت ستراكشرز محتاج الى صيانه دائميه، محتاجه الى تاكد دوري لسلامته من الصدى، من كل هذه الامور. لذلك تم اختيار البفب او UHPLC كماده لهذا الجزء، لأنه راح تحتاج فقط نصبه وهذه ما تنساه، لأنه ما عنده مشاكل بالصدى، ما عنده مشاكل بالرطوبة، إضافة إلى أنه أجزاء جدا خفيفة لأنه حجم صغير. قلنا أنه الجزء من الجسر هو جزء خرسانة تقليدية، لكن كل الجزء العكازات مع البراكت اللي راح تقوم بإسناد نقل الأحمال إلى بين الجزء الكانتليفر والحائط العمودي للجسر، كل هذه راح تكون من هذه المادة الالترا بيرفورمانس كونكريت. هذه الأجزاء راح تكون أجزاء بريكاست مسبقة الصب، في حين هذه الأجزاء البراكت راح تكون صب موقعي. لذلك في مدرسة الهندسة في فريبورغ قاموا بإجراء فحوصات كثيرة لتصميم الأجزاء المختلفة، سواء كانت العكازات نفسها وسواء البراكت. العكازات نفسها هي كانت الأبعاد اللي تم تصميمها كانت 11 سنتيم عرض مع 30 سنتيم سمك، يعني جزء جدا صغير. تم إجراء فحوصات ل eccentric loading إلها، لأنه هي راح تكون مو بشكل عمودي، فذاك تم إجراء عديد من الفحوص لاختيار الحل الأمثل. أما بالنسبة للبراكت فكان استخدام طريقة سويسرية يستخدمها من أواسط عام 2000، وهي أنه استخدام براكت يحتاج فقط إلى الفريكشن و bearing normal bearing. فكان الحل الأمثل هو هذا النوع من البراكت لتحمل الأحمال راح تكون موجودة. بالنسبة للعكازات تم اختيار شيء فورم مثل التراس، حتى لأنه كان يكون أكثر يوفر stability أكثر من لما تكون عمودية. أما عملية التنفيذ المشروع فكانت بأنه طبعا المشروع هذا الجسر هو جسر ما ممكن غلقه بالكامل، لأنه يمثل الشريان مهم جدا في بالمواصلات، لأنه واقع على الخط السريع A9. لذلك تم تحويل العمل إلى تم تخصيص جزء من الجسر من الجسرين، هو بالحقيقة المقطع من الجسرين تم تخصيص جزء من الجسرين فقط للترافيك، وتم قطع الأجزاء المتضررة من الجسر الأصلي. تم وضع صب الجزء من الخرسانة العادية بشكل كامل مع المردات. نسيت أن أذكر أنه تم زيادة عرض الجسر بحدود 40 سنتيم من كل جهة بسبب المواصفات الجديدة، وتم أيضا إضافة حديد تسليح أو ستراندز لبريستريس إضافية لهذا المكان، بالإضافة إلى بالطبع معالجة بعض التشققات الموجودة في هذا الجزء. حدث العمل كان في الجزئين، وبالتالي تم إنجاز العمل بشكل كامل. تم إنجازه أعتقد في عام 2019 بدون أن يتم غلق الجسر. فقط أحب أن أذكر أنه هذا الجسر هو رب العمل أو الميد دوفراج أو رب العمل لهذا الجسر هو المكتب الفيدرالي للطرق والجسور، وكان المكتب الإنشائي اللي قام بتصميم هذه التحديثات كانت عن طريق أنجي اللي هي مقر في لوزان. هنا مقطعين، مقطع اللي في وسط الجسر نشاهد بالأحمر هي الأشياء اللي تم إنجازها، ومقطع آخر في قريب الدعامات، لأنه البوكس جاردر هو كان أكبر بكثير بسبب أنه هناك forces lateral forces على الوولز، لذلك قاموا بربط وضع members هنا members معدنية، لأنه ممكن خدمتها عن طريق التاورز نفسها. فتم وضع هذه الأجزاء الإنشائية معدنية من أجل نقل الأحمال للجزئين. هنا صورة لعملية الإنشاء اللي تم أثناء العمل، أثناء وضع القالب، أثناء صب البيتون performance كونكريت للجزئين للبراكت ولتثبيت الأجزاء البريكاست. هنا صورة هذا حديد التسليح الموجود أصلي القديم، وهنا حديد التسليح للبراكت اللي راح تكون. تم إنجاز الجسر مثل ما قلنا في عام 2019 تم إنجازه، وكان تم إكماله بشكل كامل. الجزء المشروع الثاني أو الإكزامبل الثاني اللي أود أن أقدمه هو شيون فيادوك. كلمة شيون هي اسم للقلعة الموجودة على بحيرة ليمون، اللي هو موجود بالضبط في الطرف الشرقي لبحيرة ليمون، اللي بالضبط هو بهذا المكان. والجسر الخط السريع اللي يفوت بهذا المكان هو أي9. جسر جدا مهم لأنه هو الجسر الخط السريع اللي يربط سويسرا أو غرب سويسرا مع بقية أوروبا، اختراق جبال الألب في غران سان برنار بهذا المكان وسامبلون بهذا المكان. فيعني هو بالضبط جزء مهم جدا في شبكة الخطوط السريعة. أيضا رب العمل لهذا المشروع هو المكتب الفيدرالي للطرق والجسور. كان بروفيسور بروفيلر هو الاستشاري لهذا المشروع. المشكلة في بداية 2010-2011 أثناء الفحوصات الدورية اكتشفوا أنه هناك مشكلة للتفاعل القاعدي للخرسانة، يعني معناها الخرسانة تبدي تفقد المقاومة مالتها. فطلب أنه يتم تقوية هذا الجسر بحدود 2100 متر طول، تقوية هذا الجسر في هذا المكان. طبعا هذا الجسر مبني بين عام 1967 إلى عام 1969 مع كل هاي الثلوج وكل الأملاح اللي يتم استخدامها في لذابة الثلوج. لذلك فعلا الخرسانة كانت في وضع جدا سيء. لذلك كان القرار أنه يتم معالجة الجسر بوضع طبقة من الترا بيرفورمانس UHPLC اللي في هذا المكان. فذلك المقطع الأساسي الذي يجب أن يقوم بالتأكد منه إنشائيا هي هذا المكان في منطقة كانتليفر ومنطقة الوسط. عدة بحوث ودراسات تمت لمعرفة الحل والكومبوزيشن للماتيريال. بالنهاية كانت هناك يجب وضع 40 إلى 50 ملم فقط من UHPFRC فوق بالطبقة العلوية. في ذلك هو أولا راح يزيد من المقاومة للأجزاء الإنشائية، والجزء الثاني هو راح يوفر مقاومة أو حماية ضد الرطوبة والأملاح والمشاكل البيئية اللي راح يتعرض لها الجسر، بالإضافة إلى هو حماية للحرائق. هذه الصورة يمكن شفتوها مشابهة إلى البرزنتيشن بروفيسور تولموند. هو هذا اللي راح يكون الجوينت بين الخرسانة الأصلية الموجودة حاليا مع ال UHPFRC. تم اختيار أن يكون هناك حديد تسليح، طبقة حديد تسليح بسيطة فوق الجسر، فوق التابلية من أجل حمايتها. بعض الحسابات الإنشائية أمر عليها بشكل سريع، كيف راح تم دراستها، وتم العمل بالإنشاء. في وقتها طبعا بدأ العمل في عام 2014 2013 2014 وتم إغلاق أول جسر وأيضا هو عبارة عن جسرين. تم إغلاق أول جسر تحويل كل الترافيك إلى الجسر الآخر وتم عمل وضع إزالة الطبقات المتضررة وإضافة طبقة UHPC عليها من أجل تقويتها. ف 1200 متر مكعب من UHPC وكان عملية جدا بسيطة. هي كان عملية صب موقعي مثل ما صار. هذه هي المنشأ وهنا تشاهدون أنه عملية يبدي الإنشاء من هذا المكان ويتقدم. هنا نشاهد عملية وضع طبقة UHPC مع حديد تسليح فقط 5 سنتيم مو أكثر. بعض الصور لعملية الكيورينج. وفاينالي ختاما أحب أن أشكر مركز بحوث البناء أو دائرة بحوث البناء في بغداد وخاصة دكتورة سهير كاظم الحبوبي ودكتور محمد موسوي لأنهم ساعدوني في هذا الويبينار. إضافة إلى هذا I'd like to thank Office Federal Office or Office Fédéral de Route in Switzerland because they offered me information, and also I would like to thank Professor Broviller from PFL Switzerland and Dr. Philip Menetri from NG مقر في لوزان لمساهمتهم في هذا المشروع. Of course, I would like to thank FIB for everything. Thank you.
Thank you very much, Raad. It was clear for everybody. I hope so. We have decided to have a maximum 30 minutes of question and comments time now, and we started at once. The questions are mainly related to the presentation of François, but some can be related to Raad as well. Shall I read it and you try to give the answer, François, or how shall we make it? The first one is, what is the maximum fiber content with UHPC for FRC beams?
Well, I would say that the range of fiber content that has been used and demonstrated feasible is, let's say, between 1.5% and up to 10%, I think. So that what is possible in the laboratory. Of course, the more you put fibers, the more expensive it is, and and also the mixing issues will increase with the quantity of fibers. So I would say that the general content, fiber content, is between 2 and 3 to 3.5%, and the critical issue is whether you want a bending hardening behavior or tensile hardening behavior. I mean, hardening under direct tension, which is, for example, what is required for an overlay in restrained shrinkage situation, like you may have for the bridge decks. So we express it differently, either T3 class in French standards or in the Swiss standards, the category. But in this case, it's similar. You need to have generally more than 3% fibers. If you, I would say, only need fibers to dispense with the stirrups in a conventional beam, it's generally feasible with, let's say, between 1.7 and 2.5%. Yes, this depends also on the binder. I mean, on the matrix.
Yes. François, the way of mixing is the same. You mentioned 1.5 up to 10%. Mixing is same?
Yeah, normally the fibers are introduced when the UHPFRC matrix is fluid enough. So the longest duration during the mixing sequence is to obtain the fluid matrix, and then you introduce the fibers, and you should not have a too long time to introduce the fibers, because this produces the risk of fiber balls. And when there are 10%, the fibers may not be all of the same length. Generally, it's more efficient to have a cocktail of short and longer fibers. So I wouldn't say there is so much difference in this part of the fibers introduction.
Yes, okay, thank you. What is the optimum binder content in UHPC?
It's I would not say it's an easy question, because in the binder, in fact, because of the low water to binder ratio, only a part of the cement is hydrated. So in fact, you need cement, I would say, for the glue between the aggregate, but the aggregate is from ultrafine. You have the silica floor,
yes. Yeah.
up to, let's say, some millimeters, maybe 10 millimeters maximum, depending on the type of mixes. There is a compromise in having, I would say, coarse aggregates, because it's cheaper and you have less binder content. But these aggregates should not be the source of the defects of the materials. So I would say that a coarse aggregate has a maximum content of about 30%. Then you have sand, and this is, I would say, classically with the same content as in concrete. And then what's important is that you, for the fine parts, you have cement, you have supplementary cementitious materials and pozzolana like silica fume, or very fine metakaolin, or silica floor, which is not always inert, in fact. So that's the reason it's not easy to say it's what is binder in this, because part of the cement is unhydrated, and it's in fact it says the role of very good aggregate. The unhydrated cement, it's a buffer for the durability, also for possibility of self-healing and having additional hydration. Moreover, I would say that the different UHPFRC commercial mixes have different strategies with this respect. So, and I would say the final performance is not so much different. I would say that from in the earlier, let's say, reactive powder concrete, or I would say the first UHPFRC mixes, the cement content was between 800 and 1,000 kilograms per cubic meter. But it was progressively substituted with supplementary cementitious materials, or even limestone fillers in some cases, to limit the heat generation at early age, to limit the environmental costs and so on. I would say that we are now typically at a cement content which is closer to 600 kilograms per cubic meter. But there are SCMs and when I say cement, it's not always pure Portland cement. So you know, the ingredients in the UHPLC cookery are more numerous than before.
Yes. Next question, can you please explain the rationale for 150 megapascal as threshold compressive strength for defining UHPC?
I would say it's partly historical. I would say that it corresponds to the mixes that were feasible and on which we have the largest experience. So we have validated the design provisions with UHPFRC higher than this compressive strength. And for lower strengths, which generally correspond to higher water to binder ratios, we have not so much documentation of the of laboratory tests and validation of the structural design provisions. So I would say that this is one of the main aspects. The other aspects is not only strength, but it's also the fact that for UHPFRC with compressive strength higher than 150 megapascal, we are almost always in the higher class for durability. And so the provisions for the cover depth, the issues for chemical resistance or resistance to chlorides and so on, we really take benefit not of the compressive strength, but what is induced by this compressive strength.
Yes, exactly.
And there is a paper, I think, by Murud Belul in 2007, which really gives the figures for concrete with 150 megapascal and one with organic fibers and closer to 130 megapascal. And there is not an order of magnitude in the transfer coefficient, but there is still a difference. So with the, I would say the 130 megapascal, we are still about one order of magnitude more resistant or less diffusive than with the highest very high performance concrete covered by let's say Eurocode 2. So we are much better than C110, but there is still a difference between these materials and the UHPFRCs of 150 megapascal.
Is UHPC a sustainable material?
I would say UHPFRC can lead to sustainable solutions. And yeah, I think sustainability, we have to be careful because of course, because UHPFRC contains a lot of cement, it will be less sustainable than concrete, C20 concrete. But in your project, possibly you use 3 times less or even less. So we really have to understand sustainability for the what we call a functional unit. I'm not sure of the English words, but what's important is how you bridge a certain span with a beam. Yes. Or how you bridge a certain span for 2-lane bridge or thing like this. And if you need 3 times less material, you can, it will be equivalent for the let's say the CO2 footprint as a solution with 3 times more material. Yes. So the consequence is that if you substitute UHPFRC at the end of a project with respect to a conventional solution, it's not always sustainable because it's not always cost efficient, because if you still use more than 3 times less material, it will not be efficient. Yes. So you really have to take advantage of the lighter solution and so on, to really have the equivalence. Two other things. Oh, sorry, it's a long answer, but it's not a so simple question. Of course, I think the sustainability of the UHPFRC material has made progress from the origin. As I said, the use of SCMs is more frequent. We have, I think, the people in charge of preparing premixes and so on have taken the disadvantage. But you still need the higher cement content. So really, it's a matter of optimization of the structure itself, of the execution process. I have an example of a water channel. I mean, the conventional solution was a certain number of processed concrete segments. The thicknesses were typically 15 centimeters at least to have the post tension inside the elements, and you need a scaffolding, which is not an easy task over a river and so on. And the alternative with UHPC was only 3 segments, about 4 centimeters thick, except around the post tension. And it was the erection was feasible with a large crane at the edge of the river, and so economically and I mean, from the matter of the quantities, really the UHPFRC took the advantage very easily. And the last thing I want to say for the sustainability is how you take into account the durability. So it's not an easy task, because for the client, of course, he has to pay, and he has to say, well, it's more sustainable now, and not with all the hypotheses for the next 100 years. But from what we have experienced, the durability can also be an advantage in sustainability, because you have less maintenance, because you have less, traffic disruptions, or all the external costs of the lack of durability. But this is not always easy to take advantage of it when choosing the solution, although it's true.
Yes. The next one is a remark. Interesting remark is that the first applications of UHPC compressing strengths of 120 megapascal and 180 megapascal in Iraq were made in the late 80s as industrial floor toppings in large industrial buildings. So it is interesting. And Raad can ask in Iraq, where was this application exactly?
I cannot answer where it is, but
this is a remark. This is information. We don't need an answer. What is the background of fiber orientation factor K in AFGC? What is the source of the fixed values K global 1.25 and K local 1.75?
I have to refer on some existing papers on the subject, because but it's really based on the experience of a number of projects that I mentioned. So the Bourg-les-Valences bridge, the footbridge between the Mussem and the Fort Saint-Jean, a lot of projects on beams, on slabs, and so on. This K is a ratio between the performance of the material as measured by molded prism, let's say for the control of production, and the performance of the material in the structure itself, that is measured by sewn specimens in a representative mock-up. So it's really the experience of the collecting these values that has been used So the fact that K is higher than 1 means that in general, in the molded specimen, the fiber orientation is more favorable than in the real structure, where you have to take into account the fact that it's generally more 3D and the local value, because you take the extreme less favorable case, because it's for certain verifications where you have to take larger margins with respect to the case of a lack of fibers. Well, sorry, the values and the limitation of the values are really derived from experience. There was, I think, a question from what I read on shall we measure this K factor for every project, for every case, and so on. And I think what's underlying this question is the fact that, of course, this operation is generally, it seems to be expensive, and of course it's not so easy and it also you need some time in the project in the process of the validating the project to do this. I would mention two examples. For for beams with the same geometry and different fluidity of the mix, because there were, well, a different choice in the admixture, and in one case there were some coarse aggregate and not in the other case. So with a different fluidity and with the same fiber content, when casting the beam with one mix, we had the fibers almost horizontal, because they align with the with the free surfaces, horizontal surfaces. And in one case, because the casting was distributed and the material was more viscous, the fibers kept almost vertical. So you cannot say, well, for beams, I take this coefficient, because the result is different.
Very different, yes.
I have another case. It was the same formwork used for a footbridge in Passerelle des Anges and for the MUSEM. And the difference is that for one case, the casting was made when in one sense, and the other case one side on the other sense. And because of this, the post-tension sheetings well disturbed the flow of the UHPLC differently. And because of this, the K factor had not the same value. And so in the precasting factory, they had to readapt the way they had to cast to obtain the K value that was in the project. Mm-hmm. So I would say, well, if you cast slabs for one project and from the other with the same geometry, the same mix, you can document that probably you have not to measure the things every time. But really, for another mix and for another geometry, certainly you have to recheck. Mm-hmm. And I think it's, of course, it has a cost, but it's the way you prevent all the possible troubles during the execution afterwards.
Yes. Yes. Another question. So we have maximum 5 minutes. We have plenty of questions. We can discuss it until tomorrow morning, but I have to select some of the questions. I apologize. All of the questions are very interesting. is there any way to design the special mixture of UHPC according to the required compressive strengths?
There are, I would say, methodologies that are helpful, that are described by in a paper by François and Thierry Sedran, which is based on optimum packing. And I think mainly for the compressive strengths, these packing models are effective. I would say these models and this methodology probably need calibration depending on whether you know or well or not the constituents, because I mean the role of SCMs, the role of the ultrafine powders is not so. It's not only a physical part of meeting the strengths, but there is also the chemical aspect that is not so clearly described with these models.
Yes. Coming back to factor key, and there was no word about bowling, therefore I selected this question: how to control the key factor to prevent bowling in the concrete mixture?
I would say that the limitation of the local K value is a way of preventing bowling. That's to say, if you obtain a local K value higher than 2.5, certainly you have a so bad distribution of the fibers with local lack of fibers or local, so probably you have local bowlings. So it's an indirect way, but I would say fibers bowling has first to be prevented by the internal control in the factory. I mean, when
yes,
controlling the fresh material from the mixer.
Yes. About the tensile test, is it a direct or indirect tensile test?
Alors, in the French standards, we use an indirect tensile test, that to say bending test, and there is an inverse analysis to derive stress strain or stress crack opening design law corresponding to tension. In the Swiss standards,
yes,
the direct tensile test is used.
Yes,
I would say this was a choice mainly based on the skills of laboratories and companies of what could be, I mean, a procedure sufficiently well controlled in the country.
Yes, there is just to have a little rest for you. There is a important information here. It is, I read, then you don't need to comment. And the UHPC, UHPFRC is for performance instead of still focusing on the compressive strengths. We should mainly focus on the performance. Other properties, we agree, other properties are often as or even much more important than the compressive strengths. And by using the compressive strengths as a standard, we are still in old traditional concrete technology. Whereas how my mentor, Hans-Henrik Bacher, the inventor of the first UHPC in 1978, and the compact reinforced concrete in 1986, wrote in this typical direct way. It is a section of his saying, we have not achieved the desired safety. Many structures are unnecessarily clumsy and costly, and in relation to the new concrete, we have an unnecessarily high consumption of resources. with a corresponding unnecessarily big impact on the environment. With broader universal technology, and since we can do far better. However, to make use of the real potential, there must be a radical change of directional, complete break with conventional practice, and that connection wholesale slaughter of the sacred cows. very interesting part of remembering. Maybe one last question. Oh, very difficult because there are a lot of one. GSCE. The GSCE recommendation for ultra high strength fiber reinforced concrete and UHPLC considers material factor which consider the fiber orientation effect are the material factor in JSCE followed from Euro norms, and fiber orientation factor AFGC are the same. I don't know was it clear or not exactly.
Well, from what I know, the JSC recommendations are in the philosophy very close to the first AFGC recommendations, and I think from the way they take into account the fiber orientation, it's very similar. So of course, the evolution of the standards have made some changes or some precisions, but I think this is really a key concept that is already also present in the FIB Model Code 2010. And
yes.
So we are still with the same philosophy that we relate the material property in the structure and the material property as identified from the laboratory and control specimens.
Yes.
And I would just mention that I fully agreed with the previous comment on the fact that performance of UHP FRC is manifold term and not only compressive strength. Although the compressive strength, I mean, is an indirect sign of other things, and generally with higher compressive strength, you have higher durability and you have a higher bond of the fibers to the matrix and things like this. But in the project, it's not frequent to fully apply the compressive strength possibility. That's the reason why I think a valuable direction is pre-stressing of UHP FRC because you really take benefit of the compressive strength. But in a lot of other projects, and especially for shorter spans where you have plain UHP FRC of reinforced concrete structures made of UHP FRC, normally the compressive strength is surabundant.
Yes. Closing the question and remark session, there is a very short question you partly answered already. Are there any international standards for UHPC?
There are, for the moment, national standards in Switzerland, in France, in Canada. I think it's an informative standard, something for the moment. I think there are developments in Germany, in Spain, in the Czech Republic.
Also in Brazil, I think.
No? Maybe, yeah, maybe. Well, in the USA, they are elaborating also an ASHTO recommendation, also, but yes. It's not really finalized. So for the moment, the Eurocode revision has not addressed the case of UHP FRCs, but we have launched a process for a European standard, so not for design, but for the material specification and for execution.
Yes.
But it's the beginning of the process.
But you have mentioned earlier the effort of FIB to establish a design guide for UHPC.
Yeah. So
yes,
there is
which comes soon, within a year, I think.
Yeah, but I don't think there will be a complete design standard or substandard in the MC 2020. There are part of the recommendations, but well, you know, it's a long, it may be a long process because the experience with this material is different in the different countries, and well, we need time to understand each other.
So thank you very much. We enjoyed your answers for your questions, and we have to thank for all of the audience to send their questions. We were able to answer more or less the half of the questions, and we apologize, but we did our efforts at least to do half of them. And now we arrive to the closing. And as I mentioned to you, I will give you a chance also, all of you, first François, then Raad, to give your closing as well. My closing is that we have seen that it is a very important material from the characteristics of material and the structural performance as well. Very dense structure, high durability, high energy absorption. We have heard that even rapid hardening and so on. So a lot of positive characteristics. So we hope that we have seen already many examples of use, a very successful use in new structures and retrofitting as well. So we hope that we shall see future examples as well. So I'm happy. I was happy to organize this webinar, and I'm even more happy to participate, to be able to participate within about 3 hours altogether. It was a very, very exciting, very informative webinar, and I'm very happy that this webinar is recorded. Well, thank you for Raad initiating this webinar. Thank you to François to giving the main part of the presentations with a lot of experiences in both of your cases. And thank you for the participants as well. So I give you, François, first the chance to give your closing, please.
Yeah, thank you. So I would like to join my my gratitude to the organizers and FIB for having giving this opportunity. I would really express my pleasure of saying that I think UHPLC is a chance for concrete. When I was a young engineer, there was an advertising from the members of the concrete and contractors saying, well, it was the shape of a gray elephant, and saying we have to see concrete not like this large animal. We have to see it attractive, and I think UHPLC has made it possible to see concrete as an attractive material, and also a solution for sustainable concrete issues and works and structures. So that's really was what I wanted to share. I just have a technical question. I think some of the people in the question and answers asked for papers and references. So I had not time to give this now, but if IB can send me the question, I will try to reply. So it's
yeah, in the case when it was listed in the question and remarks, FIB can give you these questions. Yes, yes.
Yeah, thank you very much. I will need the address.
Yes, the email address. Yes,
the email addresses or something like this. But yes, I think the FIB secretariat is the
yes, very kind of you. Thank you very much.
Welcome.
Raad, please, your closing.
Yeah, thank you very much. Well, I'm very grateful for FIB for that you organized this, you adapt this webinar. For me, it's very interesting, very important to construct this bridge because engineers not just build walls, but we build bridges to connect people, both bridges in physical sense or in philosophical sense. So I think in illustration in Iraq is very difficult. After many wars, the infrastructure is exhausted, and I feel that with this material, with such simple webinar, we can give ideas, opportunities to do something there. So this is part of this effort, and I hope that this webinar is not the final final goal, but it's just a beginning gate for a beginning to maybe to propose for research, for studies, for investigations. So I hope that maybe I hope the engineers in Iraq or in the Ministry of Construction or Building Research Center to push it forward in this direction, because I think there's a solution for many problems there. So I'm very thankful for you, and maybe I try to continue doing such salon of information. Thank you very much.
Thank you for your enthusiasm. And we hope that the information was important for all the participants, and especially the engineers in Iraq. And we are very happy about that. So thank you very much. Goodbye. See you again.
Thank you.
Goodbye.
Thank you.
Thank you for everybody. Goodbye.
Bye.